Welcome back, physics fans, and here we are with the third lesson in the electrostatics chapter, and it is on electric potential energy. So we define electric potential energy as, in a similar way that we do gravitational potential energy. We say that the electric potential energy is the work that must be done to move the charge from near a larger charge. So we have a fixed larger charge, and we're going to move the smaller charge out to infinity. And we're going to calculate how much work that requires, and that'll be the change in potential energy. Now remember, in gravity, we had a force that was an inverse square relationship, and when we tried to find the work, we had to actually graph it out and get the area underneath that to get the formula. So that's going to be very similar to electrostatics because the formula is the same in inverse square. And we had to get the area under the work force distance graph. And we ended up with potential energy is equal to negative gmm over r. Negative, we set the potential energy to be 0 at infinity. Well, that's the same for electrostatics. It's k q q over r. K is the constant, q's are the charges, and r is how far it is from the center of the object of one charge to the other. Now that's how much work it takes to move it out to infinity. Now you'll notice a slight change, okay? But I'll talk about that in a second. Hang on. In this one, it's a scalar. It's not a vector. Unlike the other two that we've done for the electrostatic force, which is Coulomb's law, it was a vector, and we had to decide it by logic. We had the electric potential, and we decided by a rule what a positive test charge will go. But these were both vectors, and we decided the direction by logic. We didn't include the charge. Here, it's scalar. We have to include positive and negatives. Okay, KQQ over R. So this is the potential energy with respect to infinity, where potential energy is 0 at infinity. And by this relationship, unlike charges, have a negative potential energy, because one of these will be negative, and it'll be a negative potential energy. And that makes sense because it's going to be very much like the gravity. When we had two objects that attracted like mass or charges, it would take energy to push them apart. Okay, and that's why there's a positive here, and gravity has a negative, because this is an attraction. To make this attraction, one of them has a negative, so that's where the negative comes out. Okay, and we have to put in our signs. Try an example. Find the potential energy of a negative 75 microcoulomb charge that is 3 centimeters from a 120 microcoulomb charge, and they're attracted. Okay, so we write the equation, so let's just get going on this. So A potential energy equals KQQ over R, 9 times 10 to the 9th. Q is 75 microcoulombs, but it's negative. And we have to worry about the negative. And this one's a positive 120 microcoulombs. And we divide that by the 3 centimeter difference. Okay, and when we plug that all in, Okay, and remember this is 120 times 10 to the negative 6, and this is negative 75 times 10 to the negative 6. Mr. Calculator will say negative 2,700 joules. Write the work energy question. If that was to be moved out to infinity, how much work would it be required? So work is the change in potential energy plus the change in kinetic energy. Okay. We're moving it at a constant speed, so there's no change in kinetic energy. Okay. And then C, calculate the work done. The potential energy final minus the potential energy initial. That's 0 because it's going off to infinity. And then we have to subtract the initial potential energy, which is negative 2,700. So it'll take 2,700 joules to move it off. It's attractive force, so it will take energy to push it apart. Let's do a provincial exam question here. What is the electric potential energy of an electron at a distance of, sorry, that many meters from the proton? So it's a Bohr model here. Now, what we see, what I'm training you to, and here it is, it says energy. Look for the question, see when it says energy, boom, you know what formula you're using. K, Q, Q over R. 9 times 10 to the ninth, negative 1.6 times 10 to the negative 19th. Okay, that's the electron. And the proton, 0.6 times 10 to the 19th, still negative. And when you plug that into the Mr. Calculator, you get a negative. So we worry about signs with this formula, and it'll be 4.347 times 10 to the negative 18th joules. A. Okay. So when we have like charges, it becomes a positive potential energy because it takes work to overcome the electric repulsion and push the charges together. So example 2, find the work required for an external agent to place a, that's us pushing it, taking this charge and pushing it from infinity to a distance of 5 meters. Okay, everything's going to be initially at rest, and this guy is fixed, held in position. Okay, so the work is going to be the change in potential energy plus the change in kinetic energy. We're at a constant speed, so that's 0. And that's going to be potential energy final minus potential energy initial. And that is 0 because we're starting at infinity. So this is pretty simple at this point. Work is going to be just the potential energy final, which is KQ over R. So this is going to be 9 times 10 to the 9th, 1.75 times 10 to the negative 3 coulombs. And the other one is 2.5 times 10 to the negative 3 coulombs over a distance of 5. And Mr. Calculator, when you plug that on in, comes up to be 7.875 times 10 to the 3rd joules. Positive, because they don't want to go there, you have to push it. Thanks for watching. We will look at the rest in the next video.